Hello, my name is James Rand. I'm a PhD student at the University of Bath in the UK, and I'm doing a PhD as a mid-career, midlife update to try and transition more towards being a lake scientist than an engineer. I'm looking at underwater vehicles and mobile automation, how that could help to improve monitoring of lakes. Unfortunately, the pandemic has really mucked that up. So I've been looking at existing data sets and trying to look at problems within monitoring. And this is a story of one of the problems we've discovered. So the data set we used is from a group of lakes up at the Belgrade Lakes in Maine, USA. They're administered by the Seven Lake Alliance and Colby College as the watershed organisation up there. And it's a seasonal monitoring programme, and we've got about 4 years worth of data that we used. The data we've used from the Seven Lakes are a weather station located on the shore of Great Pond. There's also an automated data buoy on Great Pond measuring temperature, chlorophyll, dissolved oxygen, and photosynthetically active radiation PAR. There's also a manual sampling program on all of the Seven Lakes, and among other parameters, they actually do a profile weekly during the high season. Either side of the high season goes to twice a month, and then there's monitoring at the low season before ice cover happens. So looking at the monitoring data, it was clear that the sampling was regular or almost regular, and we looked at the correlation between that and weather, and we formed a hypothesis that did weather and we chose the parameters of rain, wind speed and air temperature, did that bias the manual monitoring program, the when sampling took place. So we used our 4 years of data, and we've built a logistic regression model using the parameters of those weather parameters, the yes and no of when sampling take place, and also there was a temporal element of was it a weekday or a weekend, and a weekend when manual sampling didn't take place. So we built this regression model, and it popped out, the numbers popped out quite clearly that weather appeared to drive the sampling program. So, but the problem was that this data is temporal in nature, and monitoring events aren't independent of one another. So temporal autocorrelation was always going to be an issue. So we used different and progressively more sophisticated models to address these issues. So we used a lag-dependent variable model and a GLAMA model eventually. GLAMA generally is considered the best for these temporal autoregressive problems. So these are the marginal effect plots, the results of our logistic regression modelling of all three models. The x-axis is the weather parameter that we've taken, and the y-axis is broadly represents the probability of a manual sample being taken. So as we can see, for the air temperature, the higher the air temperature, the greater the probability that sampling happens. For the wind speed, the higher the wind speed, the lower the probability of manual sampling happen, and the same relationship for rain. The higher the rainfall, the less probability there is that sampling will happen. And our broad conclusion is that good weather increases the probability of manual sampling taking place, and bad weather decreases the probability of sampling taking place. Well, I'm sure you're all sitting there going, well, that was obvious. And you're absolutely right. It's not a startling discovery, but we have quantified the effect of weather and the bias it has on the manual sampling program. But the really important question, which I'm now going to go and present, is does this bias have an effect on what we actually collect as lake scientists in a manual sampling program? So our hypothesis is that weather biases the manual sampling program, and that this biases the data collected by the manual sampling program. So we use data from Great Pond only. That's because the data buoy is located there, and that gives us our truth of our water quality parameters. And we use the manual sampling data, which is collected adjacent to that data buoy. We did it in two methods. I'm going to cover one in detail and the other I'm going to discuss briefly. So the one I'm going to talk about is we used emulated manual data, so data from the data buoy. And the other one is we actually used the actual manual sampling data. So the emulated data, the how and the why. We obtained the manual emulation data set from the automated data buoy. So when on the exact time when manual sampling took place, we took the water quality parameters from the automated data buoy set. And we ended up with 4 years worth of manual sampling data, which we could compare with 4 years worth of automated data that covered the whole entire day. And then we can compare the two. Now, while this is a powerful analysis, it actually addresses the very valid questions of calibration of the two different sensors. What about sensor drift over time? Are the sensors actually in the same location? Have they drifted apart? And because we've used this single data set, we actually eliminate all those questions, and we're purely looking at the difference between the time that manual sampling took place and the general 4-year population. So here we have a summary of statistics of our analysis, our t-test analysis. And what it shows is we've got the variables at the different depths. We've got the difference between the manual values recorded and the automated values recorded, and we have our various t-test confidence statistics here. Note very low p-values, especially for dissolved oxygen and temperature, giving us a high degree of confidence on these results. And what we see is there is indeed a difference between all the parameters with the exception of chlorophyll at 6 meters. What you'll notice, especially on temperature, I think is good, there seems to be a depth effect. So above 9 meters or so, we are seeing about a 1 degree difference between the two different methods of measurement. And below 9 meters, we're seeing about a 0.4 degrees difference between the two methods of measurement. And I'll come on to that later on. So these are the takeaway results summary of the previous table. So yes, it does appear that the weather does bias the data collected on a manual sampling program. Water temperature is about 0.4 to 1.2 degrees higher, we've discovered. DO measurements are recorded at lower, between 0.8 and 0.4 milligrams per litre. And chlorophyll at the 2 metre depth was measured at 2 micrograms a litre higher. The PAR did not meet the criteria for us conducting t-tests. It was just so scattered, so we didn't do it. And these results are sort of fairly intuitive that, well, we've got a higher water temperature, which means a lower dissolved oxygen, capacity to carry dissolved oxygen, and warmer water encourages the chlorophyll growth, so you'd typically see it higher. We also did the same analysis using the actual manual water quality sampling data. And there are various issues with this, that we're using two different instruments, a data buoy and a manual sampling probe. So, are they calibrated? Do they measure the same thing? Has the sensors drifted, especially on the data buoy? Do the sensors measure the same thing in the same location, or is there a drift effect? These various problems we addressed, but we couldn't really reconcile and give a statistically robust answer on the dissolved oxygen. The sensors are notoriously fickle, require calibration before and after use. So we ended up just using the temperature data. Now, we're confident that the boat actually ties up to the data buoy, so we think the data is co-located when it goes through the water. And temperature sensors are factory calibrated, and so the manufacturers claim don't drift and don't require further calibration. So we did various statistical tests to show that we had the same data from the two sources, or that it was the same data type. And so we performed the analysis. We did encounter problems with sensor lag, which we had to eliminate. And that's actually the cause of the depth discrepancy, the difference in data, the 9-meter point that I alluded to earlier on. Anyway, using the actual manual data, and we did t-tests and we used a Bayesian method here, we can see we've got low p-values. Here is our the difference between the automated and the manual, and we've got very similar, about a 1 degree and about 0.5 degrees, above and below that 9-meter point, above and below the thermocline, as we decided. And that's where we are seeing this effect of the sensor lag going through the thermocline, and that's where we think this data discrepancy comes from with depth. Now, this is the killer graphic for this presentation. We've got in the open red triangle the automated data buoy. We then got our manual sampling in the solid red, and we've got the manual collected data, the actual manual data, in the blue. And we can clearly see, that's sensor lag corrected, by the way, and we can clearly see, especially in the top layer, this wide variation between the two. Going down, we got to about the 9-meter point where we say, we think the sensor lag, and going through the thermocline, and we end up with more stable temperature down, and we've got this offset of about 0.4, 0.5 degrees below the thermocline. And this is the summary, really, of our work. So yes, we think there is a weather bias, and it certainly affects the manual data collected. So our headline conclusions on this piece of work is that weather conditions significantly bias the water quality data collected by manual sampling programs. While this was a case study, we think it's probably generally applicable to other lakes and other manual sampling programs. On the basis of the magnitude of the water temperature bias we found, it's typically within the root mean squared error values of lake models reported in the literature, which is why we think this is a significant finding and should be taken into account. So our recommendation is that the methodologies that we've employed are used to evaluate and correct for any weather bias on manually collected data that you use. Well, that concludes my presentation. It just remains to thank NALMS for inviting me here, and also for the generous travel grant, which unfortunately didn't get me to Oklahoma City, but there's always next year. And of course, it goes without saying that no work is done in isolation, and I must thank all the various collaborators that I've had on this piece of work, which hopefully will be published in a journal very shortly. So thank you very much for listening. Goodbye.